what elemental structure you should assume. You assume thin cylindrical sheets, then different cylindrical sheets, there are different radii. Then what all the current that enters here, so shall I say it will branch, no? It will branch. The current open here, it branches into different cylindrical sheets. So how all the sheets are, they're parallel. No? The sheets are, they're parallel, that one. So here I'll assume a sheet. So first we'll define the resistance of that particular sheet here. So let R be the radius of that, already it's indicated here. So current density is not normal to this sheet, will be along this surface of the sheet. So everywhere here, the current will be flowing into this one here. On the surface of sheet, the current will be flowing. I think I can't show the diagram, only you're supposed to assume like this. So like this, you assume another sheet, then what to current in those two sheets will come and branch, no? So therefore these sheets, the cylindrical sheets, no, or the cylindrical shells are parallel. So this, what is the assumption now? Thin cylindrical shell. So if you assume two thin cylindrical shells, what will be the current in them? Will branch out. So therefore all those cylindrical shells of varying radii, they are parallel. So first we'll define what is the resistance of this. dr is equal to. But we don't know anything about the resistivity, no? So I'll do one thing. I'll take help of J equal to E by rho. So what is J equal to? J equal to J naught R square. E by rho, that one. So further, what is E? The value of E, let me substitute here only. 1 by rho. E is what? Potential difference per unit length or potential difference by length. So finally, what is rho is equal to? Rho is equal to V J naught L R square. This will be the value of rho. So let me define now the resistance of the thin cylindrical shell. So dr is equal to rho. So how this will be the thickness dr. What is the effective area? The effective area should be 2 pi r into L. Value of rho will be V J naught L R square 2 pi RL dr. So this everything will end up. dr is equal to potential difference V 2 pi J naught L R to power of minus R dr. Zero to A, let me take it. Is it justified, anybody? Really, it's somehow I just made you to enter into the problem. Is it justified this? As a teacher, really, I want to make you think here. That's why I just brought equation, because there's a common routine way of integrating things, no? Now look at the shells. If you assume two thin cylindrical shells, how they're parallel, no? So what is the effective resistance when they're parallel? 1 by R dr it should be. 1 by R dr. I think this particular problem you came across where it was there in this one, thermal conduction. There, since the idea of the series parallel, you didn't add much, no? That's why maybe the teacher might have not discussed.
Sir? Can we also use J equal to I by A and then integrate for I?
You just wait for answer. See, then you analyze your method. So what is the effective resistance? 1 by R should be equal to 1 by dr. And there's a lot of difference there writing this equation. Why I should do like this here? Because the current year what pen will branch out. So don't show J like this. That become previous problem. In the end, you can analyze your answers. Because again, I have to explain the total problem. Nothing but let me continue here. So what is dr now? So now here I'll substitute it. This should be, why I should do like this? Because all the cylindrical sheets, cylindrical shells, they are in parallel, no? So what is the effective resistance? 1 by R equal to 1 by R1 plus 1 by R2 plus 1 by R3. That I'm integrating. So here you substitute now. Rho, this should be dr equal to rho dr.
Sir, L, sir.
Huh? What happened?
Capital L. Rho L. Along the axis, we should take the length now.
Oh, okay. So sorry, this one. Huh? Yeah. You are saying capital L? Huh?
Yes, sir.
Okay. Fine. That will be rho into the current will flow here. So length rho L. This is okay. I brought it here. This one. And what should be this one? Rho LE. So what is area? 2 pi R dr. The dr I could have shown here. I just shown it here. So this will become, so after substituting this, so I'll send it to numerator 2 pi R dr. And this will be, what is the value of rho? Rho will be V J naught L R square, this L. I'll scroll down. So this will become 1 by R. So 2 pi J naught LV. This will be there as it is. L will cancel out. So this will be R cube dr. What should be the limit? A to, so 0 to A. So 2 pi J naught V. So this will be R to power of 4 by 4, 0 to E. So R will become equal to 4V by 2 pi J naught A to power of 4. Nothing wrong. You do one thing. Sir, I'll just proceed in this way here. R, rho, L. You do that one. Somehow what when you'll end up with infinity. So it's very sure that there don't be any conductor which will have infinite resistance. So something our mathematical assumption went wrong. There's a one cross check is what you can keep in mind. Okay, this will be 2V. You can talk about here drift velocity. Anything about the drift velocity? How the actually electrons will move, you know. The electrons will move parallel to the axis here. J equal to J naught R square. So you assume a structure like this. You assume a disk. But in that disk, what happens? At different points, the electrons what happen? They're having different current density. They'll have different drift speed. So shall I just trouble you now with this one? Okay, what about the speed of these two electrons? Anybody? Will be same or different? At 0.192, what about the drift speed? current density is this speed is directly proportional to current density, no? So what is the current density at 1? Will be less. As you move away, normal to the axis, it increases, no? So that this speed at 2 will be more than 1. Got the idea? This one? And I'll display complete diagram. Now, this regarding this speed, you every numerical try to put effort. Huh? Okay, like this, the current density will be variable. So you just pick up problems of this different kind, that one.